Okay, good morning to all of you. From past two classes, we are discussing correlation coefficient. In our last class, we have been discussed in detail about limits of correlation coefficient, and we have been proved a theorem that correlation coefficient is independent of change of origin and scale. Okay, in detail we have been discussed. Before that, we have been discussed the introduction part of correlation about scatter diagram. These things already we have been discussed, and I told that in which way you have to maintain your note for your exam point of view, right? In our today class we are going to discuss another corollary or a theorem. We can say that if x and y are random variables and a b c d are any numbers provided only that a not equal to 0, c not equal to 0, then r in bracket a into x plus b cy plus d equal to ac by ac modulus into rxy, or you can say that correlation coefficient of ax plus by and cy plus d will be equal to ac by modulus of ac into correlation of x and y. Okay, so here you can see initially x and y are the two random variables. Okay, and here ax plus b is another random variable, suppose u, and v is another random variable, is considered as small c y plus d. So here we have to prove that correlation coefficient of this one, that means you can say correlation coefficient of u v equal to this constants ac by modulus of ac into correlation coefficient of xy, that we have to prove. It is very simple, you can see that. So in your note, first you have to write corollary or theorem. You can write theorem 2 or corollary, you can write, no problem. If this statement you have to write down, and this one. Okay, proof with usual notations we have. You do not start like this, like that. You have to here what you have to write, you have to write that we we know we know that variance of ax plus b equal to a square into variance of x. This is your sigma x square is nothing but variance of x, right? Sigma x square is nothing but variance of x. Okay, this things already we studied in our previous classes, when in our offline classes. You just check your note that this one, when we are discussed properties of variance, at that time you can check your note. Okay, in your properties of variance we have been studied that variance of ax plus b equal to a square into variance of x. At that time we have been proved. Okay, so same thing I have been written here. So only for that I written, we know that variance of ax plus b equal to ax square sigma x square or variance of x, and or you can put comma here, and variance of, this is semicolon. Okay, variance of cy plus d will be equal to variance of cy plus d. Similarly it will be c square variance of y or sigma y square. Okay, and covariance of ax plus b cy plus d will be ac into this one is nothing but your covariance of xy, right? So this covariance of ax plus b and cy plus d will be ac into covariance of xy already we have been proved in our last class. Okay, you can check here that what we done in our last class. You can check here that here we have covariance of xy equal to hk of covariance of uv. Okay, covariance of xy. So here xy is how much? See, covariance of, in our last class what we found, covariance of xy equal to hk into covariance of uv, right? So here in our last class x was how much? X was a plus hu, a plus hu, and y was b plus kv, b plus kv. So carefully you have to watch here that if we are going to consider covariance of xy where x equal to this much, y equal to this much, then the covariance of xy will be hk into covariance of u into v. That means the number or the constant which is multiplied with u, here h is multiplied with u, k is multiplied with v, that two numbers, here h, here k, came outside and we found covariance of u and v. So in this case, what it is, here we have a x plus b, that means covariance of a x plus b and cy plus d. Okay, see here in this case we consider xy as equal to this much, covariance of this will be equal to how much we found, that means hk. Here h and k are the constant which is multiplied with u and v, so hk covariance of uv we found, right? Similarly, if we are going to consider covariance of ax plus cy, it will be equal to, here a is multiplied with x. If I am going to compare this expression and this expression, here you can see that instead of u x is there, instead of h a is there, and plus here is b, here is a. So if we are going to compare this and this, we can found instead of k, here is c, v, y, instead of b, d is there, right? So covariance of this and this will be how much? Here a is multiplied with a x, so a, c is multiplied with y, so c into covariance of xy, or we can write sc sigma xy, right? Okay, so these things has been written there. Okay, so covariance of ax plus b cx plus d equal to sc into covariance of xy. Okay, so therefore correlation coefficient of this and this will be how much? Covariance of this divided by standard deviation of this one, standard deviation of this one, right? According to the definition, if we have two random variables x and y, correlation coefficient between x and y, that is your small r, equal to covariance of xy divided by standard deviation of x and standard deviation of y. So here the two random variables are ax plus b is one random variable and cy plus d is another random variable. So correlation coefficient of ax plus b cy plus d will be equal to covariance of this one divided by standard deviation of ax plus b, standard deviation of cy plus d. See, we know that sigma x square is your variance of x, okay, and sigma x is your standard deviation of x. So here standard deviation of x, sigma x, is nothing but root over of your variance of x. We can write root over of variance of x, right? So here it is written that sigma x, standard deviation of x, it can be written as root over of, here it can be written as root over of variance of x into root over of variance of y, or we can write variance of x into variance of y whole root over. This can be written. Okay, same thing we have been done here, that this is variance of ax plus b root over, instead of writing standard deviation, see coefficient of correlation coefficient r will be covariance of this one, numerator is covariance of this, divided by we have, we can write standard deviation of ax plus b, standard deviation of cy plus d, cy plus d. So instead of writing standard deviation format, we can write, see numerator is your this one, numerator is this one, divided by this can be written as variance of ax plus b root over into variance of cy plus d root over, right? Or we can write uh, the denominator can be written as variance of ax plus b into variance of cy plus d whole root over, right? Whatever written here only. Okay, so here covariance of ax plus b cy plus d, nothing but sc sigma xy, okay, divided by a modulus into c modulus into sigma x into sigma y, because here you can see variance of ax plus b is nothing but a square sigma x square, here c square sigma y square. So root over of this one, root over of this one is nothing but, we can consider plus or minus a, here plus or minus c, but initially we have been defined that a not equal to 0 and c not equal to 0, right? And here we are in general we have been written that a modulus and c modulus, then root over of sigma x square will be sigma x, root over of sigma y square will be sigma y. So this one is your sigma xy by sigma x into sigma y is nothing but your rxy. Okay, sigma xy is nothing but what? Covariance of xy. So covariance of xy divided by sigma x into sigma y is nothing but correlation coefficient of xy, and it's here multiplied with AC by modulus of AC. Here modulus of A into modulus of C, we can write modulus of AC, right? Here two conditions has been written, that this is proved. Okay, we intend to prove that this one, so here we proved, and this corollary has many applications. So here two conditions you can see, that if AC is greater than 0, if A and C are the same sign, okay, that means A is minus or C and C is minus, okay, same sign, then AC by A modulus will be plus 1. Okay, now AC less than 0, how it will be? A will be plus, C will be minus, or A will be minus, C will be plus. So the numerator will be minus and the denominator will be plus, and we are going to get minus 1, right? So these two conditions you have to write down in your note also. So here another important point also we can, you have to write down in your note, that here we consider that the random variable ax plus b, okay, ax plus b we consider. So if we are going to consider correlation coefficient of ax and cy only, okay, here the origin has been changed to minus b and minus d, okay, But if we are going to consider the random variables, only scale changed, right? We have a random variable x and its scale only changed to ax, y is changed to by. So correlation coefficient of ax and by, if we are going to consider, also we are going to get the same answer, because here you can see that plus plus b and plus d, whatever the constant has been added with this, have no effect. Okay, so here we are going to also get the uh, ac by ac modulus into correlation coefficient of x y. Okay, now another a small theorem, it is very easy, that, and also it is easily perceivable. What is that? If x and y are independent, if both x and y independent, then we know that covariance of xy will be 0, right? See, you can check your note. Already we have been discussed, whenever we discussed in our class, that covariance for 2D, these things we have been discussed. Okay, and you can check your note. Here I have been written that if x and y are independent variables, then covariance of xy will be equal to 0. Just before the properties of covariance, you check your note. Okay, so if it is so, then correlation coefficient will be equal to 0, because correlation coefficient of xy equal to covariance of xy by standard deviation of x into standard deviation of y, which will be equal to 0. Hence, two independent variables are uncorrelated. But converse of the theorem is not true. Converse of the theorem is not true. How it is? Here, another example. Okay. So, for this theorem, what you have to write? You have to write this. See, this one is your first theorem. This one is your first theorem. Okay, you just write down this is the corollary, or theorem 2 you can write. This is theorem 3. Okay, up to this much you have to write. Two independent variables are uncorrelated. Okay, then you have to write that, but converse of theorem is not true. That is, two uncorrelated variables may not be independent. So that we are going to be understand with the help of this example. Okay, so here we found two random variables, and the values of the two random variables are -3 for the x, -3, -2, -1, 1, 2, 3. For y, 9, 4, 1, 1, 4, 9. And here the expect sum of the x will be 0, and here the sum of the y equal to 28. And xy, if I am going to multiply, we are going to get the sum of the xy equal to 0, because these are required to find out the correlation coefficient. Okay, so now the mean, if we are going to consider mean of the x, it will be 0. Then covariance is nothing but 1 by n xy minus x bar y bar. Already we have been discussed in our first class, that here covariance of xy is nothing but 1 by n summation over xi yi minus x mean y mean. Same thing we have to consider. Covariance of xy is nothing but 1 by n summation of over xy minus x bar y bar. So if we are going to consider this one, here you can see that summation over xy equal to 0. Okay, and x bar we found 0, so obviously x bar y bar, or mean of x into mean of y, will be equal to 0, right? So as we know, according to Carperson's coefficient of correlation, r, correlation coefficient between x and y, this is your according to Carperson coefficient. Okay, will be equal to covariance of xy by standard deviation of x into standard deviation of y. So here covariance we found 0, so correlation coefficient we found 0, right? So here we found that x and y are uncorrelated because correlation coefficient is 0. From this above example, we found there is uncorrelated, there is no correlation. Linearly they have no correlation, right? But carefully you have to watch this data. carefully, here also written same thing, similar language. Carefully examine or carefully watch this data. Find x and y are not independent, but they are connected with a relation y equal to x square. See, y equal to x square. In this relation, they both are connected. You can see that minus 3, you just put minus 3, y will be 9, minus 2, 4, minus 1, 1, 1, 1, 2, you put 4, 3, x equal to 3, y equal to 9. So here we found the correlation coefficient between x and y, two random variables x and y, correlation coefficient we found 0. That means they don't have any correlation. They are uncorrelated with each other, but they are not independent. Here what we intend to know that the converse of the theorem is not true. Okay, you do one thing, that for this theorem you just write theorem 3 and continue to write up to this much. Continue to write this much, it will be better. Okay, it will be better that you have to continue to write this much. Okay, so here we have been proved one type by considering one example, that maybe x and y, two random variables, are uncorrelated with each other. There is no correlation with each other, but they are not independent. They, here from the example we found, they are connected by the relation y equal to x square. Hence two uncorrelated variables need not necessarily be independent. Okay, hence two uncorrelated variables need not necessary to be independent. So here we found that x and y are dependent. It is not mean that if x and y are uncorrelated, they are going to be independent. It is not always not truth. Okay, so uncorrelated variables. So two uncorrelated variables need not necessarily be independent. So a simple reason for this strange conclusion is that correlation coefficient xy equal to 0 merely merely impossible, the absence of any linear relationship between variables x and y. They may however exist some other relationship between them, that is a quadratic, cubic or trigonometric. So here I told from the initially, uh, whenever we started the correlation topic, I told that here we are searching the linear relation between x and y. Linear relation. So here this correlation coefficient is represents the relation or coupling between x and y linearly. Okay, but here from this example we found that they are linearly not linked with each other. Same thing, it has been written that a simple reason for this strange conclusion is that rxy equal to 0 merely implies the absence of any linear relationship between them. So there is no linear relationship. However, they have other relations. For this case, for this example, they have quadratic relation. So maybe some other example you can found that x and y they are not having the correlation with each other, but they are not going to be independent with each other. They are going to be depend, like x equal to y equal to x cube, or y equal to sin x, like this. Some other trigonometric way or other quadratic or cubic way they are going to be relate with each other. So here we have to stop our discussion. I suggest that in which way I told that to I told that in that way you have to write down the note, that you have to write down that this is your theorem 2 or corollary, this statement, then up to this much, then remark also you have to write, and theorem 3 up to start from here and up to end at here. Okay, so next you write down this in your note, watch carefully, write down in your note, and in the next class we are going to discuss assumptions underlying Carlson's correlation coefficient. Okay, so thank you so much for watching this video. Thank you.